Hello and welcome back to Control System Lectures. This is the second video on how to approximately sketch a root locus by hand. If you didn't see the first part, you can click on this link here in the upper corner, otherwise you might be confused when watching this video if you haven't seen that one first. We left off from the first video explaining the benefit of being able to approximately draw a root locus by hand. And my take on it is this. Being able to accurately draw one is not really a skill that you'll be using much when you're a professional engineer. Instead, though, understanding what the root locus looks like approximately, and then understanding how it would change if you added a pole or a zero in the feedback path, is really the benefit of learning the rules for drawing a root locus. With just a little bit of practice, you'll be able to look at just the open loop poles and zeros of a system, and then be able to visualize what the root locus would look like for the closed loop system without doing any math at all. So with that being said, some of the remaining 6 rules that I'm going to present here involve a little bit of math to prove. But instead of going through the math, I'm just going to state the rule as fact and then explain what this means to you as an engineer. But if you are interested in walking through the proofs, I've included a set of links in the description below to other control system videos on YouTube and to papers on the internet where you can find them. However, if you have access to Matlab or another similar graphing program, I think that the absolute best way to understand how a root locus plot looks is by just plotting a bunch of different ones for different poles and zeros of systems and just seeing what it looks like. Now in Matlab there's a few different ways to plot a root locus. However, one of the really good tools that they have is called SISO tool, which stands for Single Input, Single Output Tool. And using this tool you can add poles and zeros to it real time and just see visually how the root locus changes. And now I have a question for you guys. If you think you'd benefit from seeing just a real quick demo on how to use the SISO tool or in general how to plot root locus in Matlab, leave a comment below and let me know, and if there's enough interest, I'll put one together for you guys. Alright, now let me do a real quick recap of the first 4 rules. Remember that the first thing you need to do is rearrange your closed loop characteristic equation into this form, where the ratio of Q of S and P of S is the open loop transfer function G of S. So now the first rule states that there are as many lines as the degree of Q or P, whichever one is greater. So here I've drawn 3 poles and 2 zeros, and since 3 is greater than 2, then you know that there's going to be 3 lines. And rule 2 states that the lines will start at a pole of G of S and go to a zero of G of S. And remember that G of S is our open loop transfer function, so these are the poles and zeros of that open loop system. The third rule states that complex roots will always come in conjugate pairs, which means that when you're drawing your root locus, make sure it's symmetric about the real line. And the last rule that we talked about in the last video was just that a single line could never cross over itself. 2 separate root loci could cross and intersect with each other, but a single one never could. And now that brings us to a new rule for this video, rule number 5. Rule number 5 states that the portion of the real axis to the left of an odd number of critical frequencies, that is zeros and poles of G of S, are part of the low key. This is perhaps my favorite rule, because even though it's hard to state, it's really easy to remember graphically, and it's the first thing that I always do when drawing a root locus. The easier way of stating this rule is really just saying that every other space on the real axis between critical frequencies is part of the root locus. In this first example, I have 2 critical frequencies, a pole and a zero on the real axis, and so the root locus exists to the left of the odd numbers, or the first one only. Now if I swap the location of the pole and the zero, these are still the first and second critical frequencies, so the line still exists between them. It's just it's going to go to the right now, since it'll go from an open loop pole to an open loop zero. Now in this third example, I have 3 critical frequencies. And just like before, the locus exists to the left of each of the odd ones. You'll notice though that to the left of the third critical frequency goes off until infinity, because there are no other critical frequencies there. But between the first and second, that locus both converges into a point in between the two. And I'll explain in the other rules what happens when these 2 roots come together. Where do they go? Also, even if the critical frequencies are in the right half plane, they're still counted from the far right to the left. So you can always just fill in the line to the left of the odd critical frequencies, which would be here in this case. So you can see in that one case above, sometimes the roots come together and crash into each other and need to leave the real line in order to go search for an open loop zero. So rule 6 is kind of a simple rule that just explains how the roots leave and enter the real line. And they do this at perpendicular angles, or 90 degrees to the real line. So roots leave the real line in search of an open loop zero, and they break into the real line from an open loop pole. So rule 7 states what happens if there aren't enough poles or zeros to make a pair. Then it states that the unmatched poles go off to infinity to find a zero, and the unmatched zeros, the lines come in from infinity. So for example, if you have a system with just one pole and no zeros, then you have one extra pole, and the line goes to the left of that pole if it's on the real line here, off to infinity to search for its open loop zero. And if you have a system with two poles and no zeros, then you have two extra poles. And these two poles come together because it's to the left of an odd critical frequency. They crash into each other, they both leave the real axis at 90 degrees, and then they go off to infinity. And let's say you have a system with two poles and one zero. Now you have one extra pole. So the first thing you do is draw your lines to the left of the critical frequencies on the real axis. These two poles come together, crash into each other, they leave at 90 degrees, they circle back around to the left side of the zero, one turns and goes off to infinity, the other turns and goes and meets its pair at its zero. But notice that when you have one extra pole, you always have one line going off to infinity, and when you have two extra poles, you have two lines going off to infinity. And if I had drawn this a little differently and you had two extra zeros, then you would have two lines coming in from infinity. So now you might ask yourself, at what angle do those lines go off to infinity? If there's only one extra pole, it goes to the left at 180 degrees, and if there's two, it looks like they go up and down at 90 degrees each. But what if there's 3 or 4 or 5? Then what are the angles? Well, it just so happens that these lines go to infinity along asymptotes, and rule number 8 describes what those asymptote angles are. Just a real quick reminder here. An asymptote of a curve is a line such that the distance between the curve and that line approach zero as they go towards infinity. Alright, remember that we have as many asymptotes or lines going to or from infinity as there are unmatched pole zero pairs. And the angle of the asymptotes are dictated by this equation, where q are all of the integer numbers starting at 0 and going up to just 1 less than the number of unmatched pairs. The other part of this rule states that the centroid of the asymptotes all come together to a single point on the real axis, and they do this as what's called the center of gravity of the poles, which is the sum of all of the finite poles minus the sum of the finite zeros divided by the number of unmatched pairs. Remember that n minus m is the number of poles minus the number of zeros, which is just the number of lines that go to infinity. So this might seem difficult, but it's really not as hard as it looks. For example, the angles of the asymptotes is only dependent on the number of lines that go to infinity, which means if you have one line that goes to infinity, the angle will always be 180 degrees off the positive real axis. So you don't have to do the math for this case because you know that if you only have one line going to infinity, it's always going to go off to the left at 180 degrees. So moving on, if you have two lines that go to infinity and you do out the math, you'll see that one line goes off to infinity at 90 degrees and the other one goes off to infinity at negative 90 degrees. But now you can use the centroid of the asymptotes to determine exactly where they go off to 90 degrees. So in this case, I only have two poles and no zeros. So the sum of the finite poles is minus 2 plus minus 1, which is equal to minus 3. And divide that by the number of lines going to infinity, which is 2, and you're left with minus 1.5, which is halfway between the two. And that makes perfect sense with only two poles. But if we added another pole and another zero somewhere off to the left, we would still have two lines going to infinity. So the asymptote would still be at 90 degrees and minus 90. but those extra poles and zeros would shift the centroid in one direction or the other. Let's do one more quick example, and this time if you have three lines that go to infinity. Like in the case of having three poles. The first thing you do is fill in the lines along the real axis to the left of the odd critical frequencies. You can find the centroid for the asymptotes by summing up all the poles, subtracting all of the zeros, and dividing by the number of lines going to infinity. In this case, it's at -2. And you can do the angle equation to find out that the three asymptotes go out at angles of 60 degrees, 180 degrees, and -60 degrees. At this point, you can complete the root locus by taking the two poles that crash into each other and leave the real axis, and eventually go off to reach their asymptotes at 60 and -60 degrees. And of course, you can do the exact same thing with four lines, where they would crash into each other and you'd have four asymptotes, which in this case I think looks a little bit like a soccer field from above. Now, while the angles of the asymptotes are the same always for four lines going to infinity, the center of gravity, which is where they intersect the real lines, will be different based on your poles and zeros for your particular system. Now, I think that Rule 9 here doesn't really help you to draw the root locus by hand, but what it does, it gives you an understanding of how the roots move relative to each other. It states that if at least two roots go or come from infinity, so there's at least two asymptotes that go to infinity, then the overall sum of the roots must be constant. Let me show you what I mean by that and how it can help you. Let's say you have this system with three roots at -1, -2, and -3. From above, you know that the root locus looks like this. So the sum of the roots equals -6. And this is the sum of the roots when k equals 0, since when k equals 0, the roots start at the open loop roots. But when you start to increase k, the closed loop roots start to move. That's what these yellow x's are. But the sum of those yellow x's still needs to be -6. So you might be thinking, well, why does this matter? Why do I care about it? Well, if you increase k such that you get these root locations where the blue is, then you know that as you increase the gain further, you are destabilizing those two complex roots only half as fast as you are stabilizing this root that's still on the real axis. And this might be helpful knowledge when you're trying to pick out the right gain for your particular system. In Rule 10, you can kind of take or leave. For all of these root locus, we've been seeing how the roots move when you increase k from 0 to positive infinity. And Rule 10 is just a way of thinking of it if you want to decrease it from 0 to negative infinity. And you can do that by reversing Rule 5 and basically saying that the locus appears on the real axis to the right of all of the odd critical frequencies, and by adding 180 degrees to the asymptote angles. I'll draw out this one quick example with three poles. If you want to sweep from 0 to negative infinity for your gain, you draw to the right of the odd critical frequencies, so the first and the third. And the angle of the asymptotes are 60 and -60 off the negative real axis, since we added 180 degrees to them. And the root locus would look something like this. Now, I know that I kind of blazed through all of these rules really quickly, and I probably added more questions than answers for you. For example, you might be wondering, what about all the other rules you've seen in textbooks and online? Things like, where exactly do the breakaway and break-in points lie on the real axis? And what's the angle of departure from a complex pole or a complex zero? And where does the locus cross the imaginary axis? Or how do I figure out what value of k or what gain is associated with a particular point on the locus? And those are all good questions, but I'm not going to go over any of those rules in this video. And that's because I can get all that information from a software program like Matlab. And I'm no way saying that you shouldn't go off and try to learn these rules, or I'm not putting them down in any way. They are worth learning at a university. But I just found that I haven't had to remember them after I graduated, because knowing the exact equations for this was never something I needed offhand. I got an intuition or an understanding of these rules just by looking at tons of root locus plots. But what I did learn and remember were the 10 rules that I presented. They govern the look and the feel of the plot rather than the exact shape and size. Let me give you an example of what I mean and how you would use those 10 rules I presented to design a control system. Remember back to my video on the introduction to the root locus, where I posed this problem. Let's say you have these open loop roots at -1, and actually that should be +2. So we're trying to stabilize the system by closing the loop and using a proportional controller. But when you look at the root locus, you see that there's no gain there that could possibly get you a stable system. So the question is, how can we make this stable by adding either poles or zeros to this system to get the roots over to the left half plane? Well, we know that with two roots going to infinity, they're going to go to +90 and -90 like they are. But with just one, it's going to go to +180 or far off to the left. So if we add a 0 on the far left here, that will bend around the roots and cause one to go to the open loop 0 and one to go to infinity off to the left. So adding an open loop 0 and then choosing the correct gain has stabilized this system. But really what we've done is we've taken this closed loop system that had proportional feedback and added a real 0 to the controller to make it look more like this system. But the interesting thing about that is that that controller now has a proportional component, k times 3, and a derivative component, k times s. So really what we've done is we've created a PD controller to stabilize this system, but we did it all in the S domain. Alright, so I've rambled on far too long so far on this topic. I know that there's probably questions. If you have any questions, leave them in the section below, and I'll do my best to answer it. You can follow me on Twitter at Brian B. Douglas. Don't forget to subscribe so you don't miss any future videos, and as always, thanks for watching.